Unit 7 is all about the gases. We are going to do several formulas. The hardest part for this test is it's a bunch of word problems, and you're going to have to figure out which formula to use and go from there. So today you're going to learn one formula, tomorrow you're going to learn another one, and then do some practice, and we're going to learn two more after that. So you have to make sure you pay attention to today, because this is where most of the multiple choice questions are going to come from, is this set of notes, the very first 5 slides. From there we go into the math. You have to make sure you're paying attention to all of the details in this video. So with gases, we have pressure, temperature, and volume, all of which play a role in how your gases are acting. So we first need to go over some properties of all gases. Gases have no definite shape or volume, so this means you can put them in one container and they'll be nice and round or whatever. In that container, you take it, let's say, out of the balloon into the classroom. If we pop the balloon, where does the gas go that's inside this balloon? It's now inside the class, and it can go wherever it wants in the classroom. So it has no definite shape or volume. It can be compressed. This just means that we can take particles, gas particles, and we can push them closer together. Therefore, you're changing the volume. With solids, you can't do that. With liquids, you can't do that either. The volume of the solid or the liquid is pretty much going to stay the same unless you change its mass. With gases, you can change the volume without changing the mass. Gases are fluids. So typically when the doctor tells you to go home and get fluids, you're thinking liquids. But fluids means it can flow. The ability to flow. So this means gases and liquids are both fluids. Gases are much less dense than solids or liquids. Gases can diffuse and effuse. So diffuse means it's going to go from most concentrated to least concentrated. So this means it moves towards least concentrated. You talk about that in biology. Effuse just means it's able to escape small places or small holes. So for instance, a balloon. Let's say you get a balloon from a birthday party and you decide you want to keep this balloon. 2 months later, is it still going to look the same? No, because some of the gas has escaped from that balloon. That's an effuse. Okay. The next topic we're going to talk about is kinetic molecular theory. Now this is for ideal gases only. Scientists have developed this theory so we're able to compare real gases to something, sort of like a control group type thing. Kinetic is a type of energy of motion. So this is about the motion of molecules, the theory of motion of molecules. So there are 5 parts to it. First off, the particles themselves, according to this theory, have 0 volume, meaning they don't take up hardly any space, so therefore 0 volume. This is particles themselves. Now the overall volume, yes, they're going to take over. They're going to take up space. But if you look at one particle, they're saying it is 0 volume. Gas particles are in constant straight line motion. And pretty much what I have underlined is the main stuff that you've got to know for this. So this means your particles are going to be moving in straight lines. So if this is the container, your gas particles are going to move until they hit a wall, and then they're going to bounce off like that. Okay, they're going to keep going in straight line. Not like this. Okay? So kinetic theory says that it moves in straight lines. Sort of like the old school screensavers that used to have the bubbles and stuff in them. Then collisions are elastic. So this just means when 2 particles hit, they're going to hit each other and keep on going. They're not going to lose any motion. So the two particles will come together, hit, and then bounce away and just keep on going like they were. A car wreck is typically non-elastic because when the two cars hit, they stop. So collisions are elastic. Think about elastic bands. They can, when you stretch them, they move. Okay. There are no forces of traction or repulsion between gas particles, so two gas particles are not aware of each other and they could care less about what they are doing. So there's no sort of attraction or repulsion between the two. The average kinetic energy, KE, stands for kinetic energy, which is the energy of motion, is directly proportional to the temperature of gas. So this means if temperature goes up, kinetic energy goes up, which therefore means particles are moving faster. So the higher the temperature, the more kinetic energy, the particles move faster. The lower the temperature, the lower the kinetic energy, and the slower the particles are moving. Okay, now we need to talk about our three variables that are going to be extremely important for this unit. The first thing you need to understand is what the three are and their common units. Also, you're going to have to be able to convert. Now, we're going to convert just like we've been doing from Unit 1 to last unit and bringing it on to this unit. So first off, volume. The definition is how much space an object takes up. The common units include liters, milliliters, or centimeters cubed. So if you see any of these units in your problem, even if it doesn't even mention the word volume, you have got to know that these three units are talking about volume, so therefore you're going to label it as volume. Temperature. Now, most of the time with temperature we use Fahrenheit in America, and in this classroom we will not be using Fahrenheit. We will be using Celsius and what's known as kelvins. So for gases, which is the unit that we're on, you're going to always use the absolute temperature, which is known as a Kelvin when working with gases. So this is a conversion that you're going to need to know. It is on your reference table, so you don't have to memorize it, but you're pretty much going to memorize it probably by the end of this video anyways. So all you do to go from Celsius to Kelvin is add 273. So for instance, this past January, the temperature dropped to negative 10 degrees Celsius. What would that be in kelvins? So all you would do, okay, this is our Celsius. So all you're going to do is plug that in there and add 273. So no matter what temperature I give you at degrees Celsius, add 273 and you get it. So negative 10 plus 273 gives you 263K. Okay, that's all you do. So 5 degrees Celsius. I want to know it in Kelvin. You get 278. Okay, simple enough. Okay, pressure. Pressure of a gas is due to the gas particles colliding with their counter walls. So how much force they're putting on the walls of their container. That is what pressure is. Now, on the front page of your reference table, I've pointed this out to you before, you have a section that says standard pressure. These four values are standard pressure. And we're going to use these as conversions. So you're going to have to be able to go from 1 atm to millimeters of mercury, or 1 atm to kilopascals, or so forth. Okay? These are your conversions to go from one to the other. You do not have to memorize them. They're on the front page of your reference table. Okay, so the average atmospheric pressure in Denver, Colorado is 0.830 atms. I want to know what that is in millimeters of mercury and kilopascals. Okay, so pause first. Don't actually pause the video, but let me go back to this. ATM stands for atmospheres, not automatic teller machine. Atmospheres. mmHg is millimeters of mercury, millimeters mercury. Torr is just torr. kPa stands for kilopascals. If you just have PA, that's pascals. Okay? So, just a quick thing on that. If you see any of these units, that means therefore it is pressure. So going back to the problem, 0.830 atms, and I want to know that in millimeters of mercury. So you're going to convert just like we've been converting, and that's simply going from 0.830 atm. So if we have atms here, we're going to put atms on the bottom. What is this specific problem asking for? Millimeters of mercury, so we're going to put that on top. Then you're going to look at the values that I have up here and put them in the correct spot. So for millimeters of mercury, I'm going to put 760. With atms, I'm going to put 1. The atms cancel. Millimeters of mercury is what we need, so you simply multiply the top, divide by the bottom, just like we've been doing. Okay, you're allowed 3 sig figs because 0.830 is 3 sig figs. So your answer, and I'm going to put it right here because of space, is 631 millimeters of mercury. Now, kilopascals. I'm just going to use the exact number that we got from the problem and go to kPa. So again, we're going to start with 0.830 atm. We have atms on top, so this time we're going to put atms on the bottom again. This time we're going to kilopascals. So we simply put kilopascals on top. With atms, I put 1. With kilopascals, I'm going to put 101.3. So then we multiply the top, divide by the bottom. With 3 sig figs, your answer is 84.1 kPa. Take a second. If you have any questions about this part of the video, jot them down so you can bring them to class the next day. Okay, we learned about this last unit, STP, standard temperature and pressure. So this should not look any new. STP stands for standard temperature and pressure. These are the values that you must know. Now, you might not know them from last unit, and that's okay, but this unit you have to know the actual values that go with it because we're going to be using these numbers in the problems that we're going to do later. So when I say standard temperature, most of the time you need to know this number. That means 273 K. For pressure, it could be any of these values depending on the unit that I'm asking for. So if I ask for it ATMs, you're going to tell me 1, kilopascals is 101.3, millimeters of mercury is 760. Okay. This is the end of the video for the first one. You now need to take 5 minutes and go back through the notes and make a summary at the bottom of your notes. If you have any questions about this video, you need to put them on the side and bring them to class the next day.